So in this video, I'm going to derive the linear momentum equation for a control volume, and then I will define and apply momentum flux correction factor due to the non-uniformity of the velocity, and then I will discuss the forces that are acting on a control volume to plug them and obtain the equation. So I start with the Reynolds transport theorem, which actually transports us from the conservation law for a system to the conservation law for a control volume. In this situation, we are studying the linear momentum. This is P, which is equal to m times V. So basically, capital B for a system in the above equation is going to be the linear momentum P, and small b will be the linear momentum divided by the mass, and this will actually give us the velocity V itself. Now, for a system, what's the conservation law for the linear momentum? For a system, we know that the conservation law for linear momentum tells us that dP by dt is equal to the sum of forces acting on our system. We can write this as dmv by dt. And knowing that the mass does not change with time, then we can take it outside as a constant, and we end up with this equation, which is actually Newton's second law itself. If we plug this into our transport theorem, we will have mdv by dt equals sigma of, and this is equal to d by dt integral over the control volume of rho times v over dv plus integral over the control surface of rho times v. I'm considering the situation of a control volume that is at rest, so VR will be V itself. This is dot n dA. So that's our equation. Now we can take the right-hand side of the conservation equation of the system and put it with the control volume equation, and this is our conservation law for the linear momentum in a control volume. Now what we can do next is, first let's check out the terms that we have obtained. So our equation tells us that the sum of forces, this is the sum of forces, or the net force, whereas the second term that we have is, as usual, the rate of change, in this case of the linear momentum, within the control volume. And the third term gives us the net rate of linear momentum flow out of the control volume. This equation is actually a vector equation, unlike the other conservation laws that we have studied. And usually when we study vector equations in mechanics, what we basically do is that we split vectors into components across different directions. Now let's simplify our equation for well-defined inlets and outlets. So if I have well-defined inlets and outlets, I can now change this integral into a sum. Now let's look at the quantities we have. I'm assuming an average velocity through each outlet. So I have a constant v which I can take outside the integral. I'm also assuming a velocity that is perpendicular to the outlets and inlets, so it's along the direction of the normal. So v dot n is going to be v itself. And then I can see that I will have the integral of rho v dA, which is basically m dot, alongside with an additional vector for the velocity. So now I can rewrite my equation for the conservation of linear momentum with well-defined inlets and outlets. As usual, the small v is considered the velocity, whereas I consider capital V to be the volume in these videos. So here I'm going to substitute the integral by the sum of m dot times v over each outlet minus the sum of m dot times v over the inlets. This is my new equation, and let's now consider the situation of the actual change in the velocity. Velocity is not really uniform, and taking this as an average velocity over each inlet is not really very realistic, because then let's say for my outlet, considering the velocity to be constant, this is a uniform velocity profile. This is an approximation, and it's not very realistic because usually the velocity profile across an outlet looks like this. Well, first of all, I know that we have this developed velocity profile, so the vectors actually look like this, whereas the value that I have plugged was actually just the average of these. And this is my actual situation. But however, this approximation does not give us a real outcome from these two quantities that we have here. In fact, we will see that solving the integral, in the situation it will be rho integral of v squared dA for an incompressible fluid, the integral will always give us a greater value than the approximation. In the approximation, I simply just took the velocity to the outside, and then I got rho v average squared times AC. So seeing that the actual integral always has a larger quantity than the approximation, this allows me to actually study a correction factor. which is basically going to be the ratio of the actual integral divided by the approximation that I have used. And this will give me a constant number, which I can just multiply by the quantities that I have written here, which contain the average velocity. So now my average velocity can be just multiplied by a correction factor, which I can find by actually integrating and solving and then dividing by the approximation that I did. So you will see that you will have a linear momentum flux correction factor. I'll call this beta, and it will be equal to 1 over AC integral. This quantity here, v squared, was actually v into v dot n, right? So I will actually write this as the velocity that is along the direction of n, and I'll call it u because usually n is in the x direction. So I'll name this u, and thus I will be integrating only over the velocity profile that is along the direction of the normal. And I will divide by the average, and these two are squared in my equations, and this will be integrated over the area of my functional surface, which I have named AC here, by the way. So now we can just rewrite our equation. We'll just include these correction factors. We'll just multiply them by the equation by the values of the average velocity that we have used as an approximation. So actually, I'll have beta here and beta here. Now let's discuss the values of beta. So if I simply have a totally uniform flow, then I expect that the velocity component along the normal is just equal to the average velocity itself, and thus beta will be equal to 1. This is for a uniform flow. And then there is no need for this correction factor. We can consider now a fully developed laminar pipe flow. In this situation, you know that the profile looks something like this. If you solve for the integral, of course here u is not uniform, but if you solve the integral, you will see that beta for this kind of flow is going to be equal to 4 over 3. And the last example on the values of beta would consider a fully developed turbulent pipe flow. So in this situation, for a turbulent flow, the profile flattens a little bit. Now this will vary according to the amount of turbulence we have, which is usually defined by the Reynolds number. The values of beta will, however, vary between 1.01 to 1.04. In different problems, I can just take the average, so I'll just consider beta to be 1.02. And this way I have just considered the different correction factors for the different types of flow that I can have. Now, the next thing I can do is I can check for the first term that I have in my equation, basically our equation. That's what we got for our equation, and we of course added the beta here. Let's look at the first term, which is basically the sum of all of the forces acting on the control volume. Let's think what kind of forces we can have on a given control volume. So I can split the forces acting on a control volume into two parts: body forces and surface forces. Body forces can include the weight and any electromagnetic forces exerted on the objects. The surface forces, on the other hand, can include the pressure, of course, the viscosity effects, and other external forces that can be exerted. We might be cutting through the fluid with some external force. Now, the pressure force is always going to be normal, whereas the viscosity is tangent. The directions will be always useful for us because we're going to split our equation across different directions. So we're going to use components in order to study the equation, actually. So now our equation actually reduces to plus the viscosity forces plus any other external forces that we have. And these will be equal to d by dt integral of rho v dv plus sigma beta m dot v over outlets minus the sum of beta m dot v over the inputs. That's now my final expression for the conservation of linear momentum in a control volume.